In this video, we're going to talk about finding the length of a curve. So we can develop an integral formula for length of a curve if we assume the function has a continuous derivative on the given closed interval a to b. And you'll notice a and b are representing our bounds. So as long as that derivative is continuous on the closed interval, then we can find the arc length of the curve between those 2 points, A and B, from point A to point B, by using this formula. And what this formula here, the arc length L, is the integral from A to B of, we have the square root, and there's always going to be that constant 1, plus we have the derivative squared. And these are two of the exact same formulas written with just slightly different notation. Here we have our differential notation for derivative. But what we know is that dy dx means the same thing as f prime of x. So whatever works for you. And then, of course, if we were finding the arc length and our equation was x in terms of y, we would switch that and have dx dy integrating with respect to y, and then our bounds would turn into c and d. So let's do an example, because this is a pretty straightforward formula that we're using here. Here we're going to find the length of the curve y equals 4 root 2 over 3 times x to the 3/2 power minus 1 across the closed interval where x is between 0 and 1. So the first thing that we know we need is inside our arc length formula, we needed the derivative because we need to use that derivative and then square it. So I'm going to go ahead and find my derivative. The derivative of y with respect to x is going to be 4 root 2, 3. That's just a constant. Using my power rule to find that derivative, we're going to have 3/2 x to the 3/2 minus 1 is 1/2 power. And then the derivative of a constant is 0. So you'll notice the 3's are going to cancel. That 2 will reduce into the 4. And I have dy dx, or f prime of x, is 2 root 2 x to the 1/2. So one thing that I like to go ahead and do when I'm working through these problems is to take that derivative and go ahead and square it before I plug it into the formula. So dy dx squared is going to be 2 root 2 x to the 1/2 squared. So that derivative squared is going to turn into 4 times 2, 8, and x to the 1/2 squared, multiply those powers, you get 1. So my derivative squared is 8x. So the first thing I did was found my derivative, then I squared it. So we've got first, second. So the third piece here would just be to use our arc length formula. And my arc length L can be found as the integral from A to B of the square root of 1 plus dy dx, whatever that quantity is, squared, integrated with respect to x. So we want to notice our bounds here are 0 and 1. 0 and 1 are going to become my a and b value, and 8x, that represents my derivative squared. So let's plug this in and calculate our arc length value. So L is the integral from 0 to 1. We have the square root of 1 plus 8x dx. Now, in order to integrate this, this is kind of like a chain rule problem. So this is where we use u substitution for integration, right? If you thought about taking the derivative here, you'd have to use the chain rule. So the same way with integration, when it's something that looks like a composition, that's where we use u substitution to integrate. So I'll go ahead and rewrite this 0 to 1 as 1 plus 8x to the 1/2 power. In this situation, we can let u equal what's inside the parentheses, 1 plus 8x. And that would mean for us that the derivative of u with respect to x is 8. And that can be rewritten 1/8 du equals dx. Of course, when we do a u substitution, we always want to go ahead and change our bounds right at the beginning. So since u is equal to 1 plus 8x, if I plug in 0, 1 plus 8 times 0, and that gives me 1, and then u equals 1 plus 8 times 1 gives me 9. So this integral becomes now the integral from 1 to 9, u to the 1/2 power, and dx is 1/8 du. So this is pretty easy for us to now integrate using the power rule. I'll pull that 1/8 out in front. And integrating u to the 1/2, I'm going to add 1 3/2 and divide by that 3/2. So that gives me 2/3 u to the 3/2, and that would be integrated from 9 to 1. And of course, because I changed my bounds, I do not need to plug the x part of the equation back in. Remember, we said that u equals 1 plus 8x. I don't need to go back to that because I changed my bounds here to be in terms of u. So looking at this is 2/24 when I multiply those fractions, which is the same as 1/12. I have 9 to the 3/2 minus 1 to the 3/2. 1 to the 3/2 is, of course, 1. And 9 to the 3/2 is going to be, square root of 9 is 3. 3 cubed is 27. So I have 1/12. And then I have 27 minus 1, or 26. So this is equal to 26 over 12. I can cut both of those in half, and that gives me 13/6. That is the length of my curve between 0 and 1. So let's just kind of relate that to what we're looking at, what we just found. If we were to consider the graph of this curve, we would have something that looks roughly like this. I mean, obviously the graph extends beyond these points, but we are just concerned about what's happening between 0 and 1. So those points, those end points here at 0 and 1, we would have 0, -1, and 1, that's approximately 0.89. All right, we found the length, this length on the curve right here. And since we can find the length between 2 points, so we can find the length of what we would call the secant line here, it should be similar. And this is just a way that we can check to make sure that our answer is reasonable. So using the distance formula, which is just a variation of the Pythagorean theorem, right? We can find the length of that hypotenuse there. That would be 1 squared plus 1.89 squared. That's the length of this secant line from A to B, which is approximately 2.14. And if we go back and look, we got the answer 13/16 was the exact length of this curve. Well, 13/16, if you plug that into your calculator, that's going to be approximately 2.17, right? And so you'll notice that this 2.14 we found is slightly less, but very similar to that 2.17. So that's a real easy way for you to check and make sure that your answer is in the correct ballpark. So please Let me know if you have any questions, always by email.